Welcome to the next part of the module, which begins our discussion of the monitor object pattern that forms the basis for many concurrency libraries, applications, and services in Java and Android. This part first summarizes the challenges that the monitor object pattern addresses, and then describes its intent, applicability, structure, dynamics, consequences, and outlines some common known uses, based on material from the Posted To book and summarized at this link. To motivate the need for this pattern, and to introduce an example that we'll use throughout our discussion of this pattern, we generalize from several examples covered in previous parts of this module, where concurrent applications and services need to coordinate the interactions of multiple producer and consumer threads via a shared queue. A common problem in this type of software is that naive implementations of a shared queue will incur race conditions or busy waiting when multiple threads put and take items into and from the queue. For example, concurrent threads can corrupt the queue's internal state if it's not synchronized properly. Likewise, threads will incur busy waiting when the queue is empty or full, which wastes CPU cycles. A common solution to these problems is to apply the monitor object pattern to synchronize the shared queue in a manner that's both efficient and relatively easy to program. Earlier parts of this module have shown implementations of the monitor object pattern in the video on Java condition objects and Java built-in monitor objects. This part expands upon this earlier coverage to examine the pattern more comprehensively, using the Java linked blocking queue described at this link as a running example to make the discussion of the monitor object pattern more concrete. Linked blocking queue is similar to the array blocking queue we examined in this earlier video. A detailed comparison of the performance differences between the linked blocking queue and array blocking queue appear at this link. The monitor object pattern appears in the Posted To book. The intent of this pattern is to synchronize concurrent method execution to ensure that only one method at a time runs within an object. It also allows an object's methods to cooperatively schedule their execution sequence. This pattern is applicable under several conditions. For example, it's often the case that an object's interface methods can define its scheduling and synchronization boundaries. To separate concerns and protect object state from uncontrolled changes, object-oriented programmers are accustomed to accessing objects only through their interface methods. It's straightforward to extend this object-oriented programming model to protect an object's data from uncontrolled concurrent changes. Concurrent software is often easier to program when only one method at a time is active within an object. Likewise, concurrent software is also often easier to program when clients aren't responsible for serializing method execution in an object, since it's tedious and error-prone to explicitly acquire and release low-level synchronization and scheduling mechanisms, such as locks and condition variables. Finally, an object's methods may need to interact cooperatively during their execution. For example, if one thread must block awaiting a resource during its execution, it should be able to relinquish its thread of control voluntarily, so methods called from other threads can access the object to update the resource. When a method relinquishes its thread of control voluntarily, it must ensure that object-specific invariants hold. Likewise, it must resume executing within an object only when it's in a stable state. This diagram shows the structure of the monitor object pattern. The monitor object class exports one or more synchronized methods. To protect the internal state of the monitor object from race conditions, all clients must access the monitor object only through these methods. Each synchronized method typically executes in the thread of the client that invokes it. Java's link blocking queue, described at this link, is an example of a class implemented as a monitor object. Each monitor object contains one or more monitor locks, which are used to ensure mutual exclusion of its synchronized methods on a per-object basis. Each synchronized method acquires and releases a monitor lock when entering or exiting the monitor object to ensure its internal state is protected from race conditions. For example, the link blocking queue class uses two Java reentrant locks, take lock and put lock, as its monitor locks to protect the queue from corruption due to concurrent access. Multiple synchronized methods running in separate threads can cooperatively synchronize and schedule their execution sequences by waiting for and notifying each other via one or more monitor conditions associated with a monitor object. Synchronized methods use a monitor lock in conjunction with one or more monitor conditions to determine when to suspend and resume their processing. For example, the link blocking queue class uses two Java condition objects, notEmpty and notFull, as its monitor conditions to coordinate producer and consumer threads that attempt to take elements from or put elements to an empty or full queue, respectively. This UML sequence diagram shows the dynamic interactions between participants in the monitor object pattern. When thread T1 invokes a synchronized method on a monitor object, the method must first acquire the object's monitor lock. A monitor lock can't be acquired as long as another synchronized method in thread T2 is executing within the monitor object. In this case, client thread T1 will block until the synchronized method acquires the lock. After the synchronized method called by T1 is finished executing, the monitor lock is released so that other synchronized methods called by other threads can access the monitor object. For example, if thread T1 calls the synchronized take method on a link blocking queue, it will block until it can acquire the take lock. If a synchronized method must block or otherwise can't make immediate progress, it can wait on one of its monitor conditions, causing it to leave the monitor object temporarily. The monitor object implementation is responsible for ensuring the object is in a stable state before switching to another thread. When a synchronized method leaves the monitor object, the client's thread is suspended on that monitor condition, and the monitor lock is released atomically. Another synchronized method in another thread can now execute within the monitor object. For example, if thread T1 calls a synchronized take method on an empty link blocking queue, it will wait on the notEmpty condition. A synchronized method can notify a monitor condition, which awakens the thread of a synchronized method that had suspended itself on the monitor condition. For example, if thread T2 calls a synchronized put method to add a new element to the link blocking queue, it will notify the notEmpty condition object, which may awaken thread T1. A synchronized method can also notify all synchronized methods that suspended their thread earlier on the monitor condition. In this case, all suspended threads are awakened, and one of them at a time can acquire the monitor lock and run within the monitor object. After a suspended synchronized method is notified, its execution can resume at the point where it waited on the monitor condition. This resumption is typically performed implicitly by having the monitor lock reacquired atomically before the notified thread re-enters the monitor object and resumes execution of the synchronized method. For example, when the notEmpty condition object that thread T1 is waiting on is notified by thread T2, T1 will reacquire the take lock and continue trying to take an element from the queue. Due to the non-deterministic nature of concurrency, however, thread T1 may or may not actually have an element to the queue, which is why calls to wait on a condition object should nearly always be invoked within a loop. The monitor object pattern provides two key benefits to developers of concurrent software. First, it presents a concise programming model for sharing an object among cooperating threads. For example, concurrent access to a link blocking queue corresponds to conventional method invocations. Likewise, clients need not be concerned with explicit serialization mechanisms when invoking methods on a monitor object. A second benefit is that synchronized methods can use their monitor conditions to determine when a thread should suspend or resume its execution and that of collaborating threads. For example, put and take methods on a link blocking queue can suspend themselves and wait to be notified when internal state changes occur, without using inefficient polling, which allows monitor objects to cooperatively execute their methods in multiple threads. There are also several drawbacks to the monitor object pattern, however. One drawback occurs when a single monitor lock is used per monitor object, which limits scalability due to the increased contention when multiple threads serialize on the single lock. The link blocking queue class shows one way to improve scalability by defining multiple monitor locks, as we'll examine further in the next part of this module. Another drawback involves the complicated extensibility semantics resulting from tight coupling between a monitor object's functionality and its concurrency control mechanisms, which makes it hard to change synchronization and scheduling policies or mechanisms without modifying the implementations of a monitor object's methods. This link contains more discussion of the inherency anomaly problem related to this drawback. There are many known uses of the monitor object pattern, originating with the Dijkstra and Hoare style monitors that define programming language features to encapsulate functions and their internal variables into thread-safe modules, as described at this link. Java built-in monitor objects are based on a subset of the Dijkstra Hoare style monitors, as described at this link. Any Java object can be used as a monitor object that contains a single monitor lock and a single monitor condition, as described in the previous video in this module. Java monitor objects are convenient for simple use cases because they allow threads to serialize their execution implicitly via synchronized methods and coordinate their activities via calls to wait, notify, and notify all methods, defined on all Java objects. Although Java built-in monitor objects are not well suited for more sophisticated use cases, such as the classes in Java Util Concurrent and Android's concurrency frameworks, the monitor object pattern is still widely applied in this code, as shown in our analysis of the link blocking queue class in part 2 of the monitor object pattern video. C++ libraries also provide portable building blocks for implementing monitor objects. For example, ACE provides many reusable open source C++ wrapper facades for mutual exclusion, or mutex locks, and condition variables that are portable to many operating system platforms, as described at this link. Likewise, C++11 specifies mutex locks and condition variables that enable developers to write multi-threaded code in a standard way, as described at this link. In summary, concurrent software often contains objects whose methods are invoked concurrently by multiple client threads. To protect the internal state of objects shared by multiple threads, it's necessary to synchronize and schedule access to them. To simplify programming, it's often helpful if the interface an object exposes to its clients is the same, regardless of whether the object is shared by multiple threads or just accessed by a single thread. The monitor object pattern provides an intuitive programming model that enables client threads to share objects and cooperatively ensure their serialized yet interleaved execution sequence, as described at this link.